in the world of real numbers, 0 is nice. 0 is a number that if you add it on to any other number, you get that other number back again. And since addition is commutative, it also works this way. Sorry, my pen just erased on me all of a sudden. A plus 0 is also a. Right? This property is what's called the additive identity. Zero is the number that when you add it to anything else, you get that other number back again. Okay. Now, in the world of matrices, there's a similar thing that happens. So, for instance, suppose you've got a matrix that looks like 1, 2, 3, 4, 5, 6, and you want to add something onto that matrix so that you end up with 1, 2, 3, 4, 5, 6. What does that something have to be? Well, the way that we add matrices is component-wise. So whatever's in the first component, so first row, first column here, plus first row, first column there is first row. Well, it's got to be a 0. Likewise, in this position, the 2 plus something is 2. Well, that's got to be a 0. And the 3 plus, just plug zeros in everywhere here. You have a matrix that when added to this thing gives you that thing back again. And in fact, any 2 by 3 matrix plus 0 will be that matrix you started with back again. So we call this a 0 matrix. And for every size of matrix, any number of rows and columns, just fill it all in with zeros, you have a 0 matrix for that size of matrix. Okay. Now, there's various properties that these 0 matrices have. So for instance, here are the list of, this is again out of the textbook, this is theorem 1.4.2, that zeros, you know, if you add it to anything, you get that anything back again. Now, this is a big 0, meaning it's a matrix 0. If you subtract 0 from anything else, you get that anything. And if you take any matrix and you subtract itself from it, then you get 0. And they're also pointing out that if you take a matrix and multiply by -1 and add it to itself, then you get 0. This is pretty cool. If you take the 0 matrix times any matrix, then you get 0. This is very much like what 0 does for real numbers too, right? We were talking about addition, but from the point of view of multiplication, if you take any number and you multiply it by 0, you get that number back again. For matrices, we're saying if you take a 0 matrix here, let's say 0, 0, 0, 0, 0, 0, and I multiply it by anything, well, that can't just be anything. It's got to be anything where the multiplication makes sense. So if this has 3 columns, this has to have 3 rows, so A, B, C, D, E, F, whatever. You know, what do you get when you multiply it? Well, 0 plus 0 plus 0, 0 plus 0 plus 0, oops, 0 plus 0 plus 0, 0 plus 0 plus 0, and you get a 0 matrix. Now, notice in this situation that the 0 matrix I started with and the 0 matrix that I ended with are not the same size, but they're still both 0 matrices. So this is a little funny in that this 0 on this side may not actually be the same 0 on that side. And in fact, it looks like they have different fonts. This looks like it's not italics and this is italics, so they're kind of indicating that they might be different 0 matrices there. And this last one they offer here, this last property, if you have a constant times a matrix, so it's a real number times a matrix, and that equals 0, then either the constant is 0 or the matrix is a 0 matrix. Okay. Is that obvious? Is that obvious? Slide up a little bit here. Is that obvious? Well, let's see. If you have the result being a 0 matrix, so if you think about what is C times A, so if A is, let's just say, you know, A11 up to AMN, right? It's got all those things in there. AM1, A1N, sorry. And this is all equal to the zeros everywhere. Well, that's telling me that CA11 is going to be 0, because that would be the first entry here is going to be that thing. And then so CA12 is going to be 0, and C times A13 and so on has to be 0. Well, this is now a product of real numbers, and we know that for real numbers, if you've got a product of two things, this and that, equaling 0, then one or the other has to be 0. Now, we make the further argument that, I'm going to make this a little bigger over here. I'm going to make the further argument that if C is equal to 0, well then C is equal to 0, like we said. But if C is not equal to 0, that means that A11 is equal to 0. Now, once we know that C is not equal to 0, then it must mean that A12 is also equal to 0, and A13 is equal to 0. So either C is equal to 0, or it's going to turn out all these other numbers have to be equal to 0. So all of the A's are going to end up being 0. Okay. One thing I really want to notice here is that there is no statement about matrices. So for instance, what if I knew that A times B was equal to a 0 matrix? Right? Does that tell me anything about A or B? And the answer is no, it does not. For instance, if I take 0, 1, 0, 2, and I multiply it by, sorry, I paused, I had to think for a minute. How about 3, 4, 0, 0? Well, this is equal to, there is 0 plus 0, there is 0 plus 0, here is 0 plus 0, and here is 0 plus 0. So here's a situation where I've got two 2x2 matrices that are definitely not 0 matrices. They've got you know, different numbers in there, but their product is equal to 0. So just because you have a product of matrices equaling the 0 matrix, it doesn't mean that one or the other is equal to the 0 matrix. Okay. One other property that I want to point out here that's different about matrices and than real numbers. This is similar to the last thing we just looked at, but with real numbers, suppose you had AB equaling AC, where A is not equal to 0. Then we could conclude that B is equal to C, right, for real numbers. Now with matrices, it's not the case. Here's, for instance, 3 matrices that are definitely not 0 matrices, and B is definitely not equal to C. But if you try it, A times B is equal to this matrix, and A times C is equal to this matrix. But so this equation does not imply that B equals C. The thing is, what we're going to, with real numbers, what we would say is I can show that if I know that AB equals AC, I can get B equal to C, because what I do is I just divide both sides by A, or I multiply by the inverse of A, the reciprocal of A, right? In the sense of matrices, we'd want to do the same thing. If I could find a matrix that worked as sort of the reciprocal of A, then I'd multiply both sides by that matrix on the left, and I'd get rid of them, and I'd have B equals C. But the question is there a matrix here that's going to act as the reciprocal of A? And so that's what we got to get into next, is what do I mean by reciprocal? So rather than looking at additive identities, like 0, I now want to look at multiplicative identities, which is 1, and I will look at that in the next video.